everyone. Welcome back to PreAlgebra with Miss Betsy. We are continuing our work this week with fractions, improper fractions, and today we are going to be talking about comparing and ordering rational numbers. Now, if you happen to be using the same text as I am, we are in section 6.3 of our text on page 185. I'm using as my text PreAlgebra for Christian Schools. It's published by Bob Jones University Press. It's the first edition. Now, as always, you don't have to be using the same text to be able to gain something from this video. Before we get started talking about rational numbers, though, I'd like to know if you can tell me what it is that is the largest word in the English language. We know we have some really great big long ones. But you know what? I bet you don't know that smiles is the largest word in the English language. Well, how can that be? Well, there is a mile between the first letter and the last letter. So that's our lame joke for today. We'll go ahead and continue on with talking about what exactly is a rational number. Well, a rational number is any number that can be written in fractional form where it looks like this. We have a over b. And there are two conditions to this. A and b have to be integers. A and b are integers. That's condition number one. Condition number two tells us that b has to be different from 0, or b cannot equal 0. And why do we need to say that? We need to say that because division by 0 is undefined in our arithmetic system. So this is what a rational number is. It looks like a fraction. The numerator and the denominator have to be integers. And remember, integers can be negative numbers. And you can't have the denominator be equal to 0. So let's go ahead and look at a couple of numbers right quick and see if these are rational numbers. What if we have a whole number? What's an example of a whole number? Well, how about 4? That's a whole number. Is a whole number a rational number? Well, it doesn't look like a fraction, does it? But can it be written in fractional form as 4 divided by 1? Yes. So whole numbers are rational numbers because even though we don't typically write them in fractional form, they can be written that way. But what about integers? What if we had a negative 6? Does a negative 6 look like a fraction? Not the way we typically use it, but again, you can divide anything by a 1, you don't change its value, so even though negative 6 doesn't look like a fraction to us, it's still a rational number because it's possible to write it in fractional form when you divide by 1. So you see that any number divided by 1 doesn't change its value, so those are pretty obvious. But what would happen if we had a decimal number? Is a decimal number also equal, or is a decimal number also a rational number? Let's think about that for a minute. 0.9. Well, I said that anything divided by 1 doesn't change its value, so can I write 0.9 divided by 1? Well, no, I can't here. And what's the reason for that? The reason for that is that in our definition of rational numbers, it said that the numerator and the denominator had to be integers. So I can't fall back on dividing by 1. Well, you heard how I read that. I read 0.9 because we typically read decimal numbers with a point. But what is 0.9 really equal to if we read its proper name, so to speak? Well, don't we read the name of the digit, And we call the last place value that's at. So what is this? This is 9/10. So decimal numbers are also rational numbers because you can write them so that they look like a fraction. 0.9 is the same as 9/10. So what we've seen here, that decimal numbers, whole numbers, and integers are rational numbers because they can be written in fractional form, where you have a numerator divided by a denominator, and that denominator is different from 0. So it's important that you understand that that's what we're calling a rational number. And what we're doing in this section is we are comparing rational numbers, seeing which is bigger, which is smaller, and we're also placing them in proper order on the number line. So our book tells us that you can graph rational numbers expressed as fractions or as mixed numbers on the number line. So let's just go ahead and look at this. Once again, I have my very crooked number line here. 1, 2, -1, and a -2. And let's say that we want to graph -10/8, and we want to graph 1/2, and we want to graph 3/2. On the number line, how are we going to graph these? Well, I'm thinking, why don't we go ahead and convert these into mixed numbers? But we also remember that we want to have a fraction written in lowest terms. So if I have -10 divided by 8, that's not in lowest terms, is it? Has a factor of 2 in common, so you can divide the 10, the -10 by 2, you have a 5, the 8 by 2, and you have a 4, which gives us a -5/4. That fraction right there is an improper fraction reduced to lowest terms, but I'm seeing whole numbers here on my number line. So how else could I write that? You remember from our last lecture, we talked about converting a number from an improper fraction form to a mixed number. And we said we would divide the numerator by the denominator and write any remainder as a fraction. So when we do that, we see that -10/8 is equivalent to a -1 and 1/4. Here's a -1. We divide this into 4 spots. Our -1 and 1/4 would graph right about there. And that's how you would identify this. Except you would not write 1/2, you would write 1/4. Now, what about 3/2? Same thing here. Let's go ahead and convert this into mixed number. 3/2 written as a mixed number is 1.5. Halfway between 1 and 2 on the number line is the point 1.5. So we have 1 and 1/2. What about the fraction 1/2? Halfway between 0 and 1. And I'm sorry guys, I still have this cold, and I'm afraid I'm going to sneeze. Excuse me. So we have graphed rational numbers on the number line. So this is our first example here. Now let's go ahead and see what we want to do next. Would help if I would erase with the eraser instead of with the handle part. So you can use a number line to help you compare rational numbers. And remember that as you move from left to right on the number line, the numbers get larger. Numbers are negative towards the left. They are positive towards the right of the number line, and the numbers get larger as you move to the right-hand side of the number line. Numbers get larger. So I have 0 and here. So let's go ahead and graph some examples here. Let's say that we have -2 is less than a -1. -1 1/4 is less than a -3/8. And we have 1/2 is less than 1 1/2. And until you begin to get a good grasp of how numbers are ordered, any one of these three relationships here might look to be a little bit confusing to you. Something that you can think of when you're comparing numbers using this inequality symbol, the pointy end, the smaller end, is always going to point towards the smaller number. So let me be really particularly precise. As precise as I can be with a broad tip marker. -2 is less than a -1. -1 1/4 is less than a -3/8. 1/2 is less than 1 1/2. So let's go ahead and use that number line to compare these. Let's see what we have. We have -1, -2, +1, +2. Here we have a -2. Here we have a -1. And we said that the further to the left you are on the number line, the smaller the number gets. Or as you move to the right, the number is larger. So we see that we have a true statement here when we indicate that -2 is less than a -1. Well, what about here? 1 1/4 is less, -1 1/4 is less than 3/8. When we're not accounting for the fact that we have negative numbers here, we think, how can one whole thing be smaller than a fraction apart? Well, let's look and see. -3/8. 3/8, -3/8 is going to be between a -1 and a 0 on the number line. If we were actually to divide that number line into 8 equal places, -3, 1, 2, 3, that right there is a point -3/8. Where would -1 1/4 be? Well, here's -1, and then an additional 1/4 would take us to this point right here, which is -1 and 1/4 on the number line. And you see that when we look at the location of -1 1/4, as opposed to the location of -3/8, our number line shows us very clearly that it's true that -1 1/4 is smaller than a -3/8. And then of course 1/2 is less than 1 1/2. You know, if you have half a cookie, you have a smaller amount of cookie than your brother who has 1 1/2. 1/2 is halfway between 0 and 1 on the number line. 1 1/2 is halfway between 1 and 2 on the number line. 1/2 is smaller than 1 1/2 because 1/2 is to the left on the number line. Okay, see what we're talking about here? They're just wanting you to get a picture of what's going on. Now they're talking about how are we going to compare numbers, rational numbers, which you've called fractions up to this point. How do we compare fractions that have different denominators? For example, we have 5/8, and we want to know how 5/8 relates to 7/12. We want to know, is it less than, greater than, or equal to? Is 5/8 less than 7/12? Is it greater than 7/12? Or is it equal to 7/12? And there's a particular instructor, his name's Steve Demme, he does Math UC, and he tells us to compare or combine, you must be the same kind. So it's sort of a silly little saying, but I'm going to go ahead and write it down anyway. To compare or combine, you must be the same kind. You cannot evaluate the relative size of a rational number if you do not have the same denominator. We're not talking about the same kinds of rational expressions here. Here, one whole has been divided into 8 parts. On the opposite side, one whole has been divided into 12 parts. So what this little to compare or combine, you must be the same kind, what that's saying is that in order to compare rational numbers, you have to find a common denominator. And I'm going to take just a second here, and we're going to flip back in our book, and I'm going to tell you exactly what page to look on. This is where we are talking about finding common denominators. And this should be section 5.7. which is page 163. Let me take you just there just for a minute. Section 5.7, this is the least common multiple. And with least common multiples, this is what you're looking to find for a common denominator. I'll show you with this example right here. If we think of 8 times 1 is 8, 8 times 2 is 16, 8 times 3 is 24, 8 times 4 is 32. These are the first 4 multiples of 8. Now let's do some multiples of 12. 12 times 1 is 12, 12 times 2 is 24, 12 times 3 is 36, 12 times 4 is 48. Your least common multiple is the lowest number, the lowest multiple that those two numbers have in common. When you find the least common multiple, that's the number that we're going to use to create a common denominator. Remember, to compare or to combine, to add or subtract fractions, they have to be the same kind. They have to have the same denominator. When we have a denominator of 8 and we have a denominator of 12, they're not the same kind, so we're going to rewrite this with our least common multiple as a denominator, which is 24. Now let me show you. You decide for sure if I want to show you this. Yes, this is we're reviewing from 5.7. How you find a least common multiple. For example, we want to find the least common multiple of 8 and 12. First, what we do is we find the prime factorization of each number. 8 can be prime factored this way. so that we see that 8 is equal to 2 times 2 times 2, or written with exponential notation as 2 cubed. How are we going to prime factor 12? Well, 12 can be 3 times 4. 4 is 2 times 2. So we now see that 12 can be written as a product of prime factors by saying 2 squared times 3. Now, if it sounds like I'm speaking Greek to you right now, go back and find a video, my video or someone else's, where we're talking about least common multiple. There's an Algebra 1 video out there that would be really good for you to use for a review. Now, once you have found the prime factored form of each factor here, this is how you find your least common multiple. To find the least common multiple, this is what you do. You take each individual prime factor. We have a prime factor of 2, and we have a prime factor of 3. Because they're factors, it's not 2 and 3, it's 2 times 3. And we're going to look at this each place that they appear. We have a 2 squared, and we have a 2 cubed. And we're going to use the one with the largest exponent. So this becomes 2 cubed, and we only have 3 used one time, so it's 2 cubed times 3. So what is 2 cubed? 2 cubed is 8 times 3, so our least common multiple is 24. Now we already knew that, didn't we? Because I had written out 8, 16, 24, 32, 12, 24, 36, 48. But this is the algebraic way, or the mathematical way, to come up with your least common multiple, or to come up with what your common denominator is going to be. What did we do again? First, we prime factored each of our numbers, each of our denominators here. And we wrote that prime factorization using exponential notation. See, it's all full of vocabulary. If you've lost the vocabulary, go back and review it, because you've got to have it to be able to understand what I'm saying. We prime factored 8 and saw that that was equal to 2 cubed. We prime factored 12 and saw that that was equal to 2 squared times 3. Then, to calculate our least common multiple, we wrote each individual prime number, each individual prime factor, 2 and 3, with the biggest exponent that shows up anywhere on the 2. We have a 2 squared and a 2 cubed, so we used a 2 cubed. We only have a 3, which of course is 3 to the first, so that's all we use. Multiplied it together, and our least common multiple is now 24. Now, back to section 6.3, which I believe was page 185, maybe? 185, except we're on page 186. We have our common multiple of 24. So 5/8 times what is going to give us a fraction with a denominator of 24. 8 times 3 is 24. Because we multiply the denominator by 3, we have to multiply the numerator, because what we're actually doing here is multiplying by an expression that's equal to 1. So we have 15 24ths. Now here, we have 7 12ths times 2 over 2 gives us 14 24ths. I multiplied by 2 divided by 2 because 12 times 2 is 24. Now I have two numbers with the same denominator, and now I can very clearly tell the correct answer to this problem, and we can say that 15 24ths is greater than 14/24. And that's what you have to be able to do to compare between two fractions. Okay? Then the last thing that we talk about, John Mark, just move on to something else. Next thing that we're going to talk about when we're comparing positive rational numbers, something that they call a cross product. It's a product because it's the result of a multiplication problem. It's a cross product because we're sort of going catty-corner from each other. He wants to know if 5/8 is greater than, less than, or equal to 4/7. And what I just showed you prior to this is that you can find a common denominator for both fractions. In this case, it's going to be 56. Rewrite these two numbers as a common denominator of 56 and see which is larger, or if perhaps they're equal. Or you can compare what they call their cross products. Their cross products show up here. Just draw an X through your problem. 5 times 7, we're going to put on our left-hand side the product that contains this numerator. Okay, let me circle that. We're going to compare that to the second product. 8 times 4, 35 and 32. So the way in which the cross products compare, that's the way the fractions compare. As long as you have this fraction on the left-hand side that contains the numerator, you can say 35 is greater than 32. So 5/8 is greater than 4/7. If you had cross products that were the same, then you would say that the rational expressions were the same. Let's put something that we know is true. 3/6 is the same as 1/2. Doesn't matter if you cut a pizza into 6 pieces and you eat 3 of those pieces, or if you cut it into half and you eat 1, you're still eating the same amount. Well, let's compare cross products here. So we have 3 times 2, we're going to compare the numerator, the fraction containing the numerator, the product containing the numerator, with the product containing the denominator. And sure enough, 6 is equal to 6. What if we had two fractions that were smaller? Let's go ahead and compare something for very good ease of illustration here. Obviously 1/3 is less than 2/3. Let's check our cross products. Cross products, I'm going to use the product in the numerator. We're going to compare that to the product using the denominator as a factor. And sure enough, 3 is less than 6. So the way that cross products compare to one another, whether they're less than, greater than, or equal to, they compare in direct correlation to how the fractions compare. If the cross products, the first one is smaller than the other, same thing with the fraction. If the cross products are equal, the fractions are equal. If the cross products would be such that 6/10 is greater than 2/5, then that would be true, and we can verify that. 6 times 5 is 30, which is greater than 10 times 2, which is 20. That's the relationship between cross products and fractions. That's the end of this lecture, and I will see you next time.